So let's continue the proof from last time. Okay, so we had a curve. Curve was called, did I call it C? We call it C. We had a curve C inside x1 squared, and we had a bunch of CM points on it. Sorry? It's called V? Ah, okay, thank you. Consistency is important. Okay. We had a curve V in x1 squared. It has a sequence of CM points on it. And last time we showed that, well, for all but finitely many of these guys, that we have the field definition. Sorry, the field of, one second. The CM field corresponding to each of these pairs of coordinates was the same. And this didn't even use any assumption. If you read a special curve, then this is still true. Okay, so then what we can do is we can set so the endomorphism ring of xi sub 1 to be z adjoined ni tau I, and the morphism ring of xi sub 2 to be z. Sorry, this is n1 tau I. This is n2 tau I. Now they're both quadratic rings, where tau I. Well, but let's say where the GCD of these guys is 1. Okay. They're both orders in some maximal order. They both have some index. I take sort of the maximal order z adjoined tau I, which contains both of them, and then there's sort of index n1i and n2i inside of there. So now, sort of by class field theory, I don't want to say too much about this. We have sort of explicit descriptions, as we talked about last time, of the Galois groups that these guys generate with the corresponding quadratic field. And so if we let, if we look at the Galois groups, if we look at the field, Q adjoined x1i and x2i, then the Galois group of this over the quadratic field over Q adjoined any one of these, let's say tau I, is isomorphic to the class group of the minimal order that's contained inside both. Sorry, the maximal order contained inside both of these. Class group of the ring Z adjoined. So in this case it would be n1i times n2i times tau I. Okay? So in class field theory, let's describe these guys very explicitly. Let's see if we can get this result. Now recall we had V had degree d1, d2. d1 in the first variable and d2 in the second variable. And so it follows if you just look at this quotient, that the size of this guy is bounded above by d1. Right? Because we know that x2, sorry, by d2, excuse me. Because we know that x2i is of degree at most d2 over x1i. We know that this is the size of the Galois group that x1i generates, this is the size of the Galois group they both generate, and so the ratio must be not too big. Okay, but one can compute these guys fairly explicitly using class number formulas. It sort of depends on prime splitting and stuff like that. So I don't want to go through it very carefully. But this guy here is greater than, very uniformly, well, let me make it a little explicit. So this guy here is greater than or equal to n2i, but you got to be a little careful at the primes which divide n2i, so times the primes dividing n2i of 1 minus 1 over p squared. This is sort of at least how big this ratio is. Essentially, when you go up, it increases by all of n2, but you got to be a little careful about prime being split or non-split. And this is bigger than any power of n2i less than 1. Okay? Anyways, all we need is goes to infinity, and all of a sudden we have a bound for the degree, for the size of n2i and the size of n1i. Okay, so therefore n2i and 1i are bounded. We're going to the same sort of argument we went through to establish this, only it's a bit easier because in the same quadratic field, so everything is very explicit. Okay, so basically, these two guys have almost the same ring of endomorphisms. It's just sort of off by finite numbers. So by taking some isogenies, we're going to assume that the endomorphisms are actually the same. Okay. So you can either assume this at this point, or you don't have to, but it sort of makes the arguments clear. So we'll just work with that. All right. So what's the story now? Well, for every quadratic ring, we have this sort of torus around the class group. And what are the points we have contained? We sort of take a ring, we take this torsor, we shift it by a bit, and we look at the orbit of this shift. Right? And those are the points contained inside our V. Okay, so now the idea at this point is to use the point that's high in the custom. So the remainder of this proof, as we'll give it, will only work for the modular curve. It's not going to work for the Shimura curve, for the compact Shimura curves, which will eventually be proofs that work for as well. But it's really clever. So let tau I, this integer, algebraic integer, be sort of either root minus di, or 1 plus root minus di over 2, depending on whether di is even or not, or 1 4 or not. Okay? And so we know we have a point where one of the coordinates is this guy, and the other coordinate is some other CN point inside this field. Okay? So now we do the following thing. V projects down to x1 by other projection. So let S in x1 be the set of points such that the point infinity cross S equals equals V, let me write it this way, intersect infinity cross x1. So S is exactly the set of points which are the pre-image under the map down to x1 of infinity. Fix the first coordinate to be infinity, so the other points are what S is. Okay, so now these guys get closer and closer to the point infinity in the Archimedean topology. Which means if we take sort of a limit of those points, we have to approach one of the points in the infinity process. So what we're going to now is the following. So let me call it tau I prime. No, let me call it. This is way too hard. Zi be such that the point j of tau I comma zi, so zi is the next one, be such that this guy on the curve V, back in the curve V, right? So we know that V is an entire orbit of CM points. So we can take sort of a Galois conjugate, make the first coordinate anything we want, the second coordinate to be some other CM point. Okay, so we can take this V to V. And then by passing to a subsequence, we can assume that these points converge to infinity cross little s. For some little s and big S. Right, so again, we know the first coordinate converges to infinity because it's sort of a hard higher at the cusp. And there's only finitely many points in V over infinity, so by taking a subsequence, we converge to one of those finitely many points. Just in the usual Archimedean topology. Nothing fancy. So far we can do this for any point, right? Infinity is not yet playing a special role.
Why don't you assume that this is just that why can't they just be a lot of points that stay inside that don't go as much?
So we know that Galois group X, we don't see V is defined over Q, right? The Galois group X transitively of the CM points. And this is one of the CM points. And so by acting, you can make the first coordinate anything you want. So in particular, you can make it BCM point that's higher than the class one. It corresponds to the identity element of the class one. Yes. All right. Yeah, so we can assume this converges to this point. All right, so now we have two cases. For the proof. The first case is that little s is not infinity. It's some other point inside of x1. Case 1, little s is not equal to infinity. Okay? Now, there's two sort of ways to finish from this point. In case 1. So what we're going to do is the following. So let tau I prime equals b plus root d over a be the point in the upper half plane such that its image is equal to our point zi. We showed that sort of all CM points occur in this way. And in fact, of course, there's infinitely many choices because S to 0 will act on these guys transitively. But if you recall our explicit description, we can take A, B of size at most, not quite root D, but something like 2 root D. 2 root absolute value of Di here as well. Right, what was this used? Well, we took a ridiculous representative, and A was the norm of the representative. And by Minkowski's theorem, we can always take a representative with norm at most twice the square root of D. So that's where this comes from. Okay? So like, all we're doing is looking at the fundamental domain we described last time, sort of the usual one, for h2x1, and picking the point which lets us see it. Okay? Okay, so now we need, so let this be the case, and also let me call it, xi in the upper half plane be in the fundamental domain, f, so remember f is this guy, inside the upper half plane, such that the J invariant of xi is equal to our point little s. Okay? So basically, as tau I gets closer to infinity, this guy here gets closer to little s. Okay? So, let me just say the following. So if recall that if C, let me write it in the following way. Suppose that V in C squared is a holomorphic curve passing through the origin, and it's not a fiber. So it's neither the zero axis in this direction nor in this direction. Okay? What we want to do is describe V as a germ around the point 0, 0. Right? Now, if V were sort of a graph in one coordinate or the other, we could express one variable in V as a holomorphic, as a convergent power series in the other variable. Right? So it's not usually. So then there exists an integer D bigger than 0, such that you can write such that V is locally y equals f of x to the 1 over d for f, the convergent power series. Locally convergent. Okay, so basically Puiseux series are an algebraically closed field. Which the point is sort of V is mapping down to the x coordinate. Again, if this is a one-to-one map, then you don't need D. Otherwise, it's sort of a finite-to-one map. You take D to be the finite number, and then this unwinds that finite thing. Question? Right, so all this is to say that if one variable is pretty close to 0, the other variable also is pretty close to 0. Sort of at least as close as a power of how close the first variable is. We can't have one variable approaching very quickly and the other variable very slowly. So now since sort of 1 over e to the 2 pi I z is a coordinate for x1 at infinity, what this is saying is there exists an integer d bigger than 0, such that the distance of the first coordinate from infinity is at least the 1 over dth power of the distance of the second coordinate from this guy here. Such that the distance of the first coordinate, so which is sort of, let me use 1 over j of z instead. That's what we want to use. Such that 1 over j of tau I minus 1 over j of infinity, which is 0, is bounded below from j by j of tau I prime, so by zi, I guess, minus s to the power of 1 over d. Okay? Okay, but the point is that we've computed how small this guy is, right? This guy is roughly of size e. Well, it's either of size. Let me refer to it this way. It's either of size e to the power of root di or e to the power of root di over 2. So it's certainly, and I want the less than. So it's certainly at least as big as e to the power of 2 pi root di over 2, which is just pi root di. Okay? So now we're using the fact that the CM point of the cusp is actually very, very close to infinity. Alright? Okay, so Z minus S is like extraordinarily big. Sorry, I'm confusing myself. 1 second. J is big, so 1 over J is small. Right, so I want. Sorry. I was doing things correctly. So I want this, and I want the bigger than. Okay, yes, this is what I want. I apologize. Right. So J is big, so 1 over J is small, so the CM point is very, very close, so this guy must be very, very close to the bottom. Okay? Okay, so now we can once again switch back to sort of the upper half plane coordinates. And J is a local isomorphism, except that most ramified are 2 points. So this guy is sort of roughly the same distance as his prime, which is in the upper half plane. So as tau I prime minus xc sub I. If one of the points were ramified, we've got to sort of increase this by 2 or 3, but let's not worry about that. Okay, so this is weird. We have a very low height point, sort of very arithmetically simple point, approximating something extraordinarily well. Now there's 2 ways to finish. Case 1. So the first case is a result of Masser literally just says this is impossible using elliptic forms and logarithms. So the point is if you have an elliptic function, you can't have a rational point approximated to exponential complexity. So Masser proves using linear forms and logarithms this is impossible. Okay, I don't know how that proof works, so I'm not going to say very much about it. But you can, in fact, rule this out completely. The second thing you can do is you can say, okay, so maybe this isn't impossible, because we don't know how to prove it. So maybe it happens. But certainly the tau I prime can't be that close. right? They're all pretty small height. So they're at most, even by looking explicitly, they're at most like 1 over d apart, right? So certainly this kind of weird thing can happen at most once. You can have at most one CM point be very close to this of CI. So now all we need is some other point that's high up in the cusp, and we're good. Okay? Is that weird?
Okay. I'm just a bit confused.
Yes.
This chi I, like tau I prime minus chi I.
Yes.
Chi I is like the maps that S or something.
Yes.
And
Tau prime maps, yeah.
I guess I'm just kind of confused why it depends on I, even though like it's all like one.
Oh, sorry. It of course doesn't.
Oh, okay. Perfect.
Yes.
Yeah.
Obviously doesn't. Yes.
Right. So tau. Right. Then I think what you said makes sense. Okay.
Sorry, yes. Of course, as a definitive I. This guy is super fun. Okay. Okay, so now what we do, we still have to quote something, but it's more number theoretic. So now we use the fact, so by sort of subconvexity estimates, there exists a prime ideal I in Z adjoined tau I with P equals the norm of I of size at most di to the power of 1/4 plus epsilon. Okay. So the existence of small prime ideal is something that's of course very important. If you had GRH, you can make this arbitrarily low power, and that has many other applications, but in fact you can always do a little bit better than VI to the 1/2. You can always get it down to a square. So this is due to, this basically follows from Burgess. He proves like convexity for the Dirichlet, the real quadratic characters, and then implies this kind of thing. Okay, so I'm not going to go into why that's true, but given how that's true, what this says is there exists a CM point, not tau I, but let's call it tau I2, equals to A, so B plus root D over A, with A less than di to the 1/4 plus epsilon. In fact, anything bigger than the quarter will do. Anything less than a half will do. And therefore, if you look at the J invariant of tau I2, this is at least of size e to the power of the square root, to the power of di to the power of 1/4 minus epsilon. Okay, just again, because the y coordinate is still pretty high, at least d to the power of 1/4. Okay, the point being we have not just one point very high in the cusp, but at least 2 points very high. In fact, we can make infinitely many points. Just the egg is bigger, they're very high in the cusp. Okay, but now we can sort of do the same thing with the pre-image, with the second coordinate of V to the point Ti2. So now if we let sort of J of Ti2 and J of T prime I2 be in V, if these guys are in V, then this implies that both of these guys are very close to C, and therefore Ti prime minus T prime I2 in absolute value are bounded above by e to the minus di to the power of 1 quarter. Again, because they have to both approximate the same point c really, really well. Okay, and this is a contradiction. Because they're both of the form b plus root d over a, so they can't be that close. Okay. Questions about this? So yeah, this argument sort of won't work on a Chimura curve because there is no magical such point, such sequence of CM points which are exponentially close to any given indefinite. Okay. This is a very useful style of argument, by the way. You can also use this to prove, for example, non-vanishing results for L functions, which are Hegel characters. Recently used to prove sort of quantity divergence of unreordered modular varieties. So infinite point is useful. All right. So now let's get to case 2. So far, by the way, we've been ruling out CM points on every single curve, be it special or not. So at some point, we have to get to a case where these special curves actually show up. And that's case 2. So case 2 is this little point S is equal to infinity. Okay? So now we can write j of tau I prime converges to infinity cross infinity, where tau I prime is some other CM point that's fairly close to the cusp. So we'll write tau I prime is b plus root d over a, and assume for simplicity, for concreteness, that tau I is minus root d, right? That tau I is just root minus di. The other case follows the exact same way. Just stick with this one. Okay? But yes, now both points get very high, very close to the cusp, which means this integer a doesn't grow quite as fast as root di, root norm di. Okay, but now the idea is to apply the same argument and show that unless a is very, very small, like boundedly small, this point goes to infinity much faster than this point. Okay? So if you look at the size of j of tau I prime, this is e, this is approximately e to the 2 pi I norm root norm di, so norm di to the 1/2, divided by a. I'm just exponentiating the sort of y coordinate of this guy. Okay, but now sort of increasing a makes a huge difference because it's in the exponent. So this is like the 8th root of the first guy. So by the same argument, so by the Puzeau series argument, Puzeau series expansion, there exists a D such that this j of tau I has to be smaller than j of tau I prime to the power of d, if you keep going up. So this guy is roughly e to the 2 pi I di to the 1/2. This guy is roughly e to the 2 pi I di to the 1/2 times d over a. Right, so then a has to be smaller than d. A is bigger than d, this can't happen. Therefore, A is at most D. This is very effective, by the way, right? Fighting this integer D, that just involves taking the Puzzle series expansion around the infinity. Which we can just start doing. Alright, so therefore A is at most B, but what does it mean? Well, there's an isogeny between these two guys of degree A. Right? Because if you look at the lattices, the index of the lattice generated by 1 and tau I is just of index A in the lattice generated by 1 and tau I prime. Right? So the lattice 1 and tau I prime, so as the abelian group, mod the lattice 1 and tau I is of index exactly A. In fact, this is isomorphic to Z mod A. Okay? So therefore, the point J of tau I, J of tau I prime lies on the Hecke curve T sub A. So every large enough Galois orbit of CM points contains a point in the low degree Hecke curve. And so what this means is that if we look at C and we intersect it with all the low degree Hecke curves, we get the number infinity, which means C has to be one of them. And that's him. Right. Questions about the argument? I feel like I maybe lost some people. But if you sort of want, the original paper is extremely well written. So if you want more sort of details on this, there's a paper by Bast Edixhoven called Special Points on like the product of two modular curves. Where he basically does this argument, change it up a little, but essentially the same thing. Starting with the thing I presented last time, the Galois independence. Yes?
When you write like asymptotic to e to the whatever,
Yeah.
is it e to the 2 pi I? Or?
Oh, I'm being very vague, but let me think about it. Oh, you're saying instead of just e to the? I think it's e to the 2 pi I, right? Because J is locally Q inverse plus other stuff.
Okay.
Q is e to the 2 pi I z. The leading term is e to the minus 2 pi I z, which I think amounts to this. Yes?
Yeah, sorry, no.
Oh, yes.
What is this?
Puzzle series?
Yeah, it's been about that one.
Oh, Puzzle series is the name for this power series in x to the 1 over d.
Oh,
For
okay,
some
okay,
d.
okay.
Yeah. So I mean, one way of saying what I wrote there is that if you take locally sort of German holomorphic functions, locally converted power series, then their algebraic closure is just locally converted power series in z to the 1 over d for some integer d. That's an algebraically closed field. Yeah.
So my question is, like, can you still do something like that when you have like not just two, the power of two, but multiple ones? So
Right.
Like these are the power.
Yes, that's a great question. So the answer seems to be no. And that no just means that people have tried and failed. So as soon as Axel made this argument, Andrei was responsible for this argument primarily, actually. Axel built on it. People try to generalize it, and you can't really make it. And the reason you can't make it is if you look at the pre-image of infinity, say you have a surface in x1 squared, say. So if you have a curve in like x1 cubed, then the statement follows basically formally from this one. because you can project that curve into all the x1 squareds and you can apply the statement. So the next interesting case is like a surface in, say, x1 cubed. So you can still make, the first part is still fine. Like the conclusion that the field definition is the same and morphism ring is the same, that's basically still fine. But now what can you do? You can apply your Galois orbit and sort of move all 3 points at once, and you can make one point be an infinity. And all it does to the other 2 is it places them on an algebraic curve. And so the problem is that, okay, so these guys can't be too close, but now you don't have to be because they're not approximating any one thing. Does that make sense? So that's why the argument I presented works. Master's argument doesn't work. Master's argument doesn't work because it was important for his argument that the point S was algebraic. We were approximating algebraic, whereas now the point S just lies on some algebraic curve, so it could very well be very transcendental. So yeah, when it first came out, people, including myself, thought about it, and nobody could figure out how to do it. So it seems like it's hard to generalize it. I don't know. Yeah. Okay, so what I want to do now is I want to go to like the main proof paradigm we're going to be talking about, which is this thing introduced by Jonathan Pila and Umberto Zagni, which has become sort of the strategy of proving these sort of statements in unlikely intersections. It seems to work without any assumptions and very generally. So let's talk about the paradigm of sort of point counting plus homodymality. So we'll spend quite a few lectures sort of describing this and making it work in a variety of cases. But before we go into concrete, I want to describe the strategy that we're going to be taking, that was taken by Umberto and Zagni to prove these kind of statements. So to do that, we'll apply it to CM case eventually. But once again, let's jump back to length conjecture. It's the easiest case to talk about. So suppose that V in C star squared contains lots of roots of unity, lots of torsion points, infinitely many torsion points. So the idea behind what Pila and Zagni do is the following. They say consider the exponential map E from C to C star, which sends Z to e to the 2 pi I Z. And then, so this is like an Attell covering map, but it's transcendental because e to the x is transcendental. Because, for example, it grows too fast, proof. So one thing to notice about this is that if you look at if T in C star is a torsion point of order n, then you can write T as E of A over N, for A an integer between 0 and N. It's a very simple fact. Torsion points are images under E of the rational points. Did I screw it up? I think this is correct. Okay. Okay, so the first idea is we want to use this sort of rational structure. Do the following things. So first of all, we'll let E sub 2 be the map from C squared to C star squared. which just exponentiates. And we'll let f be the fundamental domain. So f in C squared is defined by the points of z, w, where the real part of z and the real part of w are between 0 and 1. Okay? So f is a fundamental domain for this map. Okay, so now what we do is we look at, we let sort of w be the inverse image of v under v sub 2 intersect f. Okay, so now we're putting back an algebraic curve under a transcendental map, so we get something most likely transcendental, but it's still a holomorphic sort of curve, and we only care about it inside f. And if you think about it, we sort of only need to care about it inside f, because what is it everywhere else? It is the translate of what's in f by z squared. Right? This is f is fundamental domain, so you can see sort of all of w by just looking at f. Okay, so now the idea is that V has many torsion points, infinitely many torsion points, which means that W has infinitely many rational points. Okay, so saying that more formally, so if T arrow in V is torsion of order n, then W contains sort of the inverse image of T intersecting a fundamental domain. And this guy is also inside Q. In fact, it's a rational point with the denominator n. Okay. And now we use Galois orbits again, so we know if you contain one of these points, you contain at least phi of n of them, which means W contains phi of n of these points. So therefore, intersection of W with z squared over n, this is actually, I can just write bigger than or equal to, is at least phi of n for infinitely many n. Okay? And in fact, it's a little more natural for us to just, instead of using all of W, we'll just use WR. These guys are all real, so we can restrict to the real locus. Okay, so what do we have now? We have some real analytic curve. We have some real analytic curve, right? Because it's inside sort of the unit circle squared, if you think about it properly. And it contains sort of lots of rational points, in particular polynomially many rational points. Right? These guys are all of height n, and we contain polynomially many of these guys of height n. Okay, so now the theorem of Bombieri and Pila, which we're going to talk about a lot, but there's a theorem of them which says that if W in R squared is a real analytic compact curve, and it contains polynomially many rational points, then W is algebraic, or what's more precise is to say that it's semi-algebraic. So it's compact, so it can't, well, I guess it could be algebraic, but it doesn't have to be. So it's really just means it's a compact piece of an algebraic curve. Okay. Okay. Yes, okay, well, let me leave it here for now. Okay, so for now, take this as like an axiom. Starting next class, we'll talk a lot about how this kind of thing is proven. But so as a result, what we get is our W, this is a general thing, so our W is semi-algebraic. Okay, so that's really weird. We have an algebraic thing downstairs, we pull it back, algebraic upstairs. So now, there's a statement in transcendence. Well, so now, since V into inverse of V are algebraic, V has to be a torus coset. Not a torsion coset, by the way. Right? If you take any torus coset, its preimage is linear, so it's algebraic. Okay, so then it's a torsion coset because it contains torsion points. Start with this conclusion only lets you, this assumption is only to say that it's a torus coset. Okay, so that's the idea of the proof. So broadly speaking, there's like 3 main arguments in the proof. So the first one is you have to establish large Galois orbits. Which sort of for us, if you recall so far, for torsion points, it was sort of easy. It was explicit. For Billiam varieties, we quoted the theorem of Winter-Berger to give us large Galois orbits. For CM points, at least on X1, again, it's sort of classical by Ziegel's theorem. In general, it's much harder, so it's still missing in many cases of Landry-Oort, and more generally, it's sort of the main difficult ingredient. We're not going to focus on this one, at least not yet. The second one is sort of, let me add Barbieri's name. So Barbieri, Pila, and Pila-Wilkie is this business of many rational, or actually sort of algebraic points implies algebraicity. So it turns out we can't stick to rational points. Already you can see if we try to make the same argument for CM points, the preimage of a CM point in X1 squared, in X1 is a quadratic point in the upper half plane. So you have to deal with low degree points as well. That turns out not to be a major complication. And the third thing we need is sort of transcendence results. Transcendence. Results which say that if you have something, so to speak, algebraic upstairs and algebraic downstairs, then it's one of finite numerated things. In fact, you end up needing much harder results than this kind of statement if you go beyond curves and surfaces, so we'll talk about that as well. Okay, these are the main steps for this paradigm. So, oh, wait, I've been looking at that clock, which doesn't make any sense. Okay, 2:04 makes more sense. I'm waiting. I thought it was like 9:40 for forever, and we end on the hour. All right, so I just want to mention before, so next time we'll start sort of properly speaking about this part. We'll do some algebraic points on curves theory. What I want to mention is that there's this sort of, there's this understanding that O-minimality and sort of logic, model theory, enters a lot of these results, and therefore makes them to a large extent inaccessible. So I want to point out that if you're sort of scared of model theory, it's not as central to the picture as you might think it is. So for length conjecture, you actually, if you're just doing the length conjecture or abelian varieties, you don't need any model theory whatsoever. You sort of develop this theory, and you never say the word logic, and everything works as planned. Even that's a benefit to some people. Some people like logic. The reason homonymity enters, the reason you talk about logic at some point, is in this step here. So if you have compact varieties, then the world is good. You can sort of make these kind of statements and they remain true. With non-compact varieties, the world becomes bad. So your enemy is things like y is equal to sine of x over 2 pi. So this guy is the enemy. Why is he the enemy? Well, he's not algebraic, and it contains a ton of rational points, like a ton of integer points. It contains the entire integer points on the x-axis. Okay? So somehow he's not algebraic, and he contains integer points, so you can apply this kind of paradigm. He's not compact, but you can stick to compact curves. Already in the modular case, you can see that. And so somehow we have to go to a bigger class of sets than compact varieties, but not so big that it includes bad things like this. This is sort of the only place homonymity enters the world. Okay? So we'll talk about homonymity. So we won't. Right? So it's important to keep in perspective where it comes to the argument. All right, I'm already over, so we'll resume on Wednesday.